what should I say, uh, the, uh, the, the detailed height distribution which you could realize. MSL is only an approximation of our theoretical understanding, isn't it? As I've told you many a times, there is one thing which we call it as conceptual or convention. How do we define it? And there is another way how to realize it. So the difference between the two uh, concept, which we call it reference system and reference frame. So reference system can be defined by convention. You can have your own convention, your friend can have its own convention, your teachers can have its own convention. So conventions, in fact, you must have seen convention center is there in the city. What they discuss in those conventions, they discuss about the future, they develop the conventions. But later on, after 10 years, they realize how much work has been done over those conventions. Is there any realization? So when we talk about the realization, we have to go back to reference frame. In our domain, we call it reference system and reference frame. So MSL is just one way to realize our convention. Our convention was to have a gravitational potential surfaces in and around the country so that we could work with the height network. Coincidentally, our in please switch off your microphone. Those who have not muted himself. Uh,
सर स्क्रीन नहीं दिख रहा है.
Sorry,
सर स्क्रीन विजुअल नहीं है.
screen visible नहीं?
यस सर.
नो सर विजुअल है, उनकी साइड से कोई
Yes,
इशू
sir.
है.
शुभम.
ये visual.
Now is it visible?
यस सर.
So, as I've told you, the mean sea level is just one approximation of our gravitational or just way of realizing our height distribution throughout the country. Obviously, we are lagging very much behind in establishing a proper gravity network inside our country. The reason is very simple, because the agency which is assigned to do this kind of job is Survey of India, and the agency has to take its lead. Okay. Uh, Naturally speaking, in other countries, the data sharing between agencies or government bodies and academic institution is very free. But in India, we do not have such fortunes. We have to strive very hard to get a data, access to data. So this GravD project, similar to GravD project, the Indian authorities are also planning. But let us see when our such kind of projects would be launched. The objective is very simple. The reason why we have to do it, because if you see this bottom part, the coastal region of India, so mean sea level has to be equal in both sides of the so-called coastal region. But recently, the difference between Mumbai and Vishakhapatnam uh, coastal tide gauge station, what we have got the difference of 35 centimeter in mean sea level. It has, I mean, the network, after establishing network between Mumbai and Vishakhapatnam, it has been found that mean sea level at Vishakhapatnam and Mumbai have got difference of 35 centimeter. That means this much difference is still there with the recent variations in the sea level, and we have to do a lot of you know effort to minimize this. But recently, the Survey of India has started working towards establishing this network, which we call it mean sea level, by establishing uh, these MSL points or the coastal boundaries with the gravity networks also. But still, I mean, a lot of work has to be done before we realize, just like the US has realized it. But the objective is very simple. MSL cannot serve the purpose now or in future also. MSL is just in a starting point to work with, but still you have to do a lot of effort in establishing the gravity network. And the gravity project is one such leading task in US, where they are trying to have a gravity map of whole country, whole US, whole states in throughout multiple missions. And in fact, several gravity missions have been planned, which are helping us. But since it is very true that satellite gravitational gravimetry missions are not fulfilling those desired objective as have been set, they are also looking, and in fact they have started this airborne gravity mission. And for this airborne gravity missions, they are giving this gravity map to agencies, and which is quite popular, and you can download it also. It is available on their website. You can see the data, you can visualize it, and you can work with it. So that is the difference between our country and United States, how they are moving ahead with this kind of scenario. So the gravity network development is quite essential, and in fact I'll share one paper also with you, where you could realize. Let me just I don't know whether you have seen it or not. Just give me a moment. So that you should also feel comfortable when we are discussing this topic of mean sea level. Just a minute. Yes, I'm sharing the screen again. Just please let me know if it is visible at your end or not. So I hope it is visible. You can see this. There is a very nice paper which is available on your internet, and this paper is published, presented in FIG Congress in 2018 only. And is it visible at your end?
Yes, sir.
Yes, sir.
So this talks about the towards the modernization of Indian vertical data. I'm just highlighting those content which will give you a little thoughts how we are working. So this there's a statement written is that in India the 3D geodetic.
हेलो सर, वॉइस नहीं आ रही.
Hello. Am I audible, Shumit?
Yes, sir, you are audible. Yes, sir.
So in India, the 3D geodetic datum has already been established in relation to ITRF in 2005. So when we say about the 3D geodetic datum, it is what we meant to say. We meant that the latitude longitude
or the northing, easting, and up component can be given in with reference to ITRF, but the vertical datum is slightly different. So the geodetic datum, that means how we are appreciating the international ellipsoid. So we have got our maps converted to ITRF, and in fact we have seen in one of the slide also that Survey of India has adopted this ITRF 2008. That means they have converted it to, but the vertical datum is also required. So that's why the next line says clearly a similar approach is needed for the new vertical datum realization. So this was, I mean, the cutting edge right now, that people are trying to develop this new vertical datum. And this, the present India vertical datum refers to mean sea level, which was determined more than a century ago. So please remember, this is the paper highlights that part, because you could realize that in mean sea level we started with that for 1920 the mean sea level was designed in such a manner that it should appreciate the sea level information from 1900 to 1990. So for 19 years they take the average and work that surface as mean sea level for 1920. Similarly, present also we have to work with that kind of information if we have to work in a real-time manner. So this is the region where and I've told you the geoid, which is the definition of equipotential surface, and the local mean sea level, they are deviation. The deviation is because of the sea surface topography. So that next point is also talks about that. This over the period of time, it has been realized that the local mean sea level is usually departed from the geoid. Geoid is the definition. That means it has to be the equipotential surface, but MSL is one such realization. But this the convergence of MSL as a geoid cannot be a possibility because of the sea surface topography. And in fact, satellite altimetry, there is one complete geodetic approach where scientists flown over this sea surfaces, and they get this altimetry information to develop this sea surface topography. So this the Indian vertical datum, which is still, we do not have this proper I mean, I should say proper approach towards how we are going to establish our Indian vertical datum. But if you talk about that, are we still working in that century-old datum or MSL information? The answer is no. Why? Because our system has been redefined, or the places where initially we have got the benchmark, they got revisited, and a new information has been added up in the late 1980s. And in this particular survey that lasted around 6 to 7 years, people from Survey of India have dedicatedly covered thousands of kilometers by road, so that the vertical information can be updated, so that it could be used nowadays. So, but from that onwards, we do not have such any updation. And while performing this kind of fresh adjustment of level network, now there are 2-3 inputs which are coming at this point from this paper. I'll share this paper to you so that you could read it, because very nice paper to developing your understanding in the Indian vertical datum. Because for horizontal datum, as I've told you, the 3D geodetic datum, which we talk about in terms of northing, easting, and up, the geodetic latitude, longitude, and height, we are already converted to ITRF. So now we do not have any sort of dilemma in that. We are already adopted the ITRF guidelines, which is International Terrestrial Reference Frame 2008. But still for vertical datum, we are still relying on our old network. But the demand at present, what it says, you have to go back to developing the gravitational potential kind of surfaces, which would help us in realizing the height system for a particular country. So this first adjustment, we will go through an adjustment of level network. That's why we have course of adjustment and computation. You will see from your own hands, you will solve a very nice level network problem with the help of our understanding what we are covering in the course of GDP course. That you will be given a level network where the observation would be given, and errors would be there in this level network, and that error has to be adjusted, which we will perform together in later on when we'll discuss about the adjustment part problem. But anyways, that is another thing. What is important is that a difference of 35 centimeter was reported between Mumbai West Coast and Chennai East Coast tide gauge station, with the West Coast being lower than the East Coast. So in general, that was the problem, which we still, if you try to see that we are working in such an understanding that this kind of scenario will happen, because we are the coastal boundaries are very far from each other, and the Bay of Bengal is got affected by a lot of storms. And in fact, you must have seen the tsunami of Sumatra Andaman in 2004, which has created a lot of havoc, because of which also the sea surfaces or the variation could be seen between the two ends. That is very true, and we have to account for it. So, but what they are looking in terms of how they could develop it. So in general, a concept for defining the global vertical datum has been evolved in recent time. That's the GravD project which I was talking about. It's the objective of it, that how we can improve our understanding in terms of vertical datum. So this concept suggests that a conventional mean sea level, which we call it as geoid, be uniquely specified by adopting a geopotential value, which is W naught, which best represents the mean sea level in global sense. Once a conventional W naught is adopted for global vertical datum, the individual vertical datum at regional, national, or continent level can be related to the adopted W naught by means of global gravity field model, precise ITRF positions, and leveled height. So as you could see, there are three major components that are coming into the picture, by which are talking about how this W naught can help us in defining this vertical datum. We are talking about a global gravity field model. What is global gravity field model? That means how the mass distribution is present over a continent, and how the this mass distribution is affecting the gravity values. See, the gravity varies with the mass, how the mass is distributed, or the density inside a crust is present. That will affect the gravity values. So the so-called the equipotential surfaces, for which we need this potential value, geopotential value, we need to use this geopotential value, and at the same time we also need a global gravity field model, which would be realized by either satellite missions or airborne mission, where a flight could be flown over a particular region for developing this gravity field model. At the same time, you need precise ITRF position, which nowadays it's considered as within 1 mm kind of thing. We have this kind of precision at present in ITRF positions, and as well as the leveled heights, which must allow a proper transformation into the corresponding geopotential number. So with the help of these all 3-4 quantities, what we are trying to do, we are trying to have a equipotential number that is varying within the country. That is our objective is. So in order to implement the above approach of realization of modern vertical datum for Indian subcontinent, a project was initiated by GRB branch, and in the present scenario, it has been planned to define the Indian vertical datum in terms of geopotential value, which is W naught, which we call it LVD. Okay, and at 8 numbers of tide gauge observatory located in 4 on east coast and 4 on west coast. And what we are doing the GNSS observation at all tide gauge stations, and they have tide gauge benchmarks. They have done the height difference, which needs to be computed, because you have to convert from ellipsoidal height to orthometric height, because ultimately you have to work with orthometric height. Ellipsoidal height cannot be taken for granted. So height difference, that is obviously the between from the ellipsoidal edge and orthometric edge and geoid n, and height will be adjusted according to the in order to estimate the geopotential value. So this kind of work we are, we would be looking forward in next few years. Maybe we'll have more publication from GRB branch. Recently, we had a meeting, I think in somewhere in August, where they are sharing the data set for course stations. That means they are planning to establish a course network. That means continuously operating reference station throughout the country, and they are planning to share the data set. So I have applied for that. Let's see whether they will be in position to have an access to through the portal or something like that. So in principle, the residual part of the height difference correspond to the offset between geopotential value used in the selected global geoid model and the local potential value. So apart from this, the computation of W naught will also be carried out using molodensky theory, which is another domain of going with the gravity understanding. So this is very nice paper. I'll just share this paper to your teams so that you could have an access to. It's very nice paper. For more understanding, you have to go through the complete, but with your basic theory, which I've covered in this recent 2-3 discussion, nowadays it is very easy to go through that complete paper. But this is very recent paper that has been published by Survey of India, and in fact, the person SK Singh is, I think, one of the GRB head or the director of GRB branch who has published this work. Anyways, we'll get back to our old understanding. Just a minute.
Sir, voice is not coming.
So many of you would be trying to read more about MSL and its basics, because it's very interesting, because most of the content you can follow very quickly. But what is the problem is that where to find the relevant content. So one of the basic course, which we call it physical geodesy, that talks about the gravity, is unfortunately is not being taught in majority of the Indian institutions. This is one such drawback which we have to overcome soon. And I'm planning to have this course from next semester, let's say from July onwards, whether we'll be able to develop the understanding to teach this subject at postgraduate level, because this is very much relevant. Next future is about how you're handling the gravity data for majority of the public work, maybe be it climate studies, be it hydrological studies for geoscience purpose. A lot of understanding would be developed on physical geodesy. So let us see what we are reading right now. It's part of the geometrical geodesy. That means we are trying to use the geometrical shapes for answering the question in terms of relating the surfaces using the equations for solving certain uh, for unknowns or certain quantities. So we are using the surfaces for measurements. So that's why we are in this domain of geometric geodesy, which we are very popularly and very commonly we are following it. And in fact, it has been taught at various places. And apart from this basic domain of physical geodesy and geometrical geodesy, what we are covering in terms of techniques that we are mostly following, or you will be seeing in next semester also, that will be part of space geodesy. In space geodesy, what is happening, we are trying to see how the earth is monitored with the help of space missions. That means your space mission, be it low earth orbit, medium earth orbit, geostationary orbit, so all kind of missions that are launched by, in fact, airborne also. So we are doing this in any instrument that are placed in any orbits or satellite missions. We are doing earth measurement for understanding various concept, various geometry related problems that will part of the space geodesy. So these are the popularly three branches of geodesy where we need to contribute a lot. Although from space point of view, we are contributing in GNSS, we are contributing in INSAR, we are contributing in LiDAR, but there are other domain also. That is just one popular is VLBI, another one is SLR, there is one called LLR. The VLBI is known as very long baseline interferometry. So what we are doing in VLBI is there are very large telescopes are placed in various different continent, and they try to follow quasars. The quasars are a radio source, an extragalactic source that is very far from Earth. And if you see from this place, your Earth would look like it's stationary. So what is their objective is that they try to detect those radio sources to finally detect the shift between this distance between two points that are very far from each other. So they are trying to form a very long baseline interferometry. That means this distance is not very 100 or 200 kilometers. It could be 1,000 or could be 2,000, 5,000 kilometer kind of thing. So if you establish such kind of network and you follow those extragalactic radio sources, you try to work for understanding the various motions that Earth has to go through. And in fact, more largely, it talks about the Earth rotation. So we are working or using VLBI for Earth rotation. Then there is a technique called SLR. SLR is satellite laser ranging. A satellite laser ranging means where it is an active remote sensing where satellite is there in the space, and with the help of laser ranging, you are trying to use those beacons on that are placed on the surface of Earth. But that SLR is used for defining the center of gravity of Earth, which is very popular or very much required for defining a coordinate system. Similarly, you have LLR, which we call it lunar laser ranging. So these are very popular space geodetic technique. But although we are focusing only GNSS, INSAR, and LiDAR, last year we had one meeting at IIT Kanpur regarding how to initiate this the so-called VLBI program in India. And soon we are going to submit one. IIT Kanpur is leading this project, and soon they will be submitting this project to Government of India for establishing 3 VLBI station in coordination with ISRO. And if we are having data from these stations, we can more contribute towards Earth rotation. So that is very much required nowadays, because if you try to see the VLBI station all over the globe that is established through the IVS, which is called as International VLBI Service. So if you see the map of IVS, we do not have any station in India or in Pakistan or Bangladesh or Nepal, but majority of the tectonic process is happening around us. We have Himalaya, which is active zone in terms of earthquakes. The fault movements are very active. We have Sumatra Andaman, which is an active the fault which through which tsunami has occurred. So we need to do this because we are lagging behind from several years. We do not have any such station in our India, so we need to develop it. So we are working towards it. Let's see in future we are doing it. We are getting something out of it or not. Anyways, so as I've told you, these are the domains where uh, we are uh, we are focusing, and in fact, there are a lot of expectation is also from Indian scientific community to propose certain type of structure, knowledge structure in this domain also. Coming back to your own discussion, yes, we have to focus on physical geodesy, but again, there is a lot of content which is available on so-called internet where you can read more about the gravity understanding. Okay, so MSL and ellipsoidal height, I hope it is very much clear. We'll discuss little more about coordinate system before we go back to map projection, and then your laboratory on total stations will be started by our students. So now I hope everybody is very much clear about MSL and ellipsoidal height. See here what we are representing at point A and point B are there. The H1, capital H1 and capital H2 are the height above mean sea level. So H1 is clearly greater than H2. But on that same point on ellipsoid, you have H2 greater than H1. So that's why the the understanding with respect to ellipsoid and geoid cannot be clubbed together until unless you have information about geoidal undulation. So your relationship, which is sorry, which is that means the geoidal undulation would serve the purpose only and only if you have the understanding about the variation in the geoidal undulations. So this is a very nice representation where you need to realize that height alone from ellipsoid cannot serve your purpose, because GPS nowadays is available to everyone. What you need a gravity models like EGM08 you have, where you can sufficiently reduce to orthometric height with respect to getting ellipsoidal height. So from GPS, if you work with a GPS, you will get a small h. What you want to work in a local system, you need the capital H. For getting capital H, what you need UN. N would come from gravity or models which are available or missions which we are planning, or it could be space-based mission, which right now we have. What are the space mission which would help us? Grace follow on. An old one mission is called Champ mission. These are all mission, although the Grace is more dedicated towards gravity mission. Champ is more for hydrological understanding. Okay, so our little discussion that we started on mean sea level have given a little more introduction towards importance of gravity understanding. Let us see what we were discussing. Okay, so this next figure, which is discussing about how to find the so-called oblate and prolate ellipsoid. So you have ellipsoid. You know what is the properties of ellipsoid? You have major axis, you have minor axis, and you have flattening. These are the three fundamental mathematical quantities through which you can have better uh, understanding about an ellipsoid. But what is more important is how one ellipsoid, which we found out that is representing the Earth surface or best fit an Earth surface, can be developed. So there are ellipsoid can be developed in two types. One is called as oblate ellipsoid, another is called prolate ellipsoid. So generally it is called as your Earth is an oblate ellipsoid. But how to develop such ellipsoid? So if you have an ellipse whose major axis, major axis is this, minor axis is this, and if you rotate this ellipsoid with respect to this so-called minor axis, you will get oblate shape of ellipsoid. But if you rotate from this major axis, you will get prolate. But since we are more interested in this oblate ellipsoid, that's why the in literature, if you read, our literature is completely filled up with so-called uh, the so-called oblate ellipsoid theories. And in fact, you need to understand this part also, that your oblate shape theory came into existence somewhere around, if I'm not wrong, around 16th century, when there was a mission by French expedition, we call it, is uh, they have a lot of data which have been collected between Peru. There is a place called Peru and another one, I forgot the name. Between that two places, they have conducted a lot of experiments, which is very popularly known as 16th century French expedition. And in that particular expedition, it was realized that your Earth was oblate ellipsoid. Okay, and that has to be represented by oblate ellipsoid. So that's one basic understanding. But how to achieve from mathematical point of view is that you rotate your ellipse with respect to minor axis, then you realize this oblate ellipsoid. And there is one basic theory on, although I don't know whether it would be useful or not, but it is introducing a coordinate system which is nothing but xz with origin halfway on the line on f1 f2 and z-axis perpendicular to f1 f2. This is one we're calling about. We see that if point P is on x-axis, then that constant is equal to twice the distance from P to origin. This is the length of the semi-major axis. Call it as 2a, which is nothing but the two foci, which is f1 and f2. This point P is there, so P f1 P f2 throughout on any point on this ellipsoid would give the twice of semi-major axis. Obviously, because of the prolate ellipsoid, also it is possible. Okay, so but anyways, this is just one basic concept. What is more interesting is to understand the meridian concept, which is very much popular for better understanding. So this figure is representing the oblate ellipsoid, which we have discussed. And what we are doing right now, we are trying to develop certain conceptual understanding about the meridians, or the direction in prime vertical. How to achieve that? For that, this figure is presented. You could see and realize this is your. I'm just drawing. I don't know whether it is why it is a little bit hanging. So this is your, let's say, axis. We will need to focus more, or discuss more. Uh, then only we'll realize. So this is your axis. Okay, and this is your Earth. This is your equator. This is your equator. Okay. This is, we call it meridian. That is joining 0 degree to 180 degree. This is called as meridian. Meridian can be drawn at any points, and in fact, it is you could call it the line of longitudes. Okay, so this meridian that is joining the North Pole and South Pole, and it has to go through that point which we are interested in. So let's say this, there is a one point which we are interested in. So we will go through. Oh, sorry. Yes. So we will go through this point from this point, having that point to South Pole. So this point is called as any point on the surface, but that line that goes through from North Pole containing this point and goes to South Pole is called as meridian of the point. So this is simply meridian. Then you have a latitude lines, which is in literature is also called as parallel circles. That means line of equal latitude. And similarly, if a perpendicular which is drawn on this through this point, it will meet the equator at some point. Please remember the difference between two things. One is called as geodetic and another is called as geocentric. So geocentric will, what is the difference between geocentric? That normal which you would be drawing here would reach to center. When this will be a possibility? This will be a possibility only and only if your Earth is represented by a sphere. If your Earth is represented by a sphere, what will happen? If you select any point and if you draw a perpendicular to it, it will reach to center of that sphere. Then it would be called as geocentric. The geodetic one, that's why this difference of terminology is there. In geodetic one, it will not reach to the center. Instead, it will meet any point on the equatorial surface or equator. What is equator? Equator is surface which you can better recall. If you cut down Earth into two pieces from center containing the center, the equator contains the center. Okay. So if a plane that cuts the Earth into two parts, then if the center is contained in one of the section, that is called as equator surface. So this perpendicular would meet on the equator, and line angle that is in anti-clockwise will be called as latitude. Obviously, line joining center of so-called center of mass of Earth and that intersection point on the equator with respect to meridian, this angle is known as lambda. So I'm again redrawing after releasing all this heavy drawings so that you could better appreciate it. So what we are doing, we are trying the normals, which is more important. Now you know the meridian, what we call it meridian. So you have this point, this is point meridian, this is normal, and this is line joining center of mass of Earth to that intersection point. This is lambda, this is phi. So lambda is known as longitude, phi is known as latitude. This lambda is also measured from sometimes what we call it as 0-degree longitude line or Greenwich meridian. Where somewhere at this point, a telescope has been fitted that watches the 0-degree north here, and that's why this point, the meridian which contains this observatory, I think this observatory is placed somewhere in UK and named as Greenwich. And this observatory, there's a telescope, there may be the axis of the telescope is watching this north. That's why this point containing the meridian is called as Greenwich meridian. It's also known as 0-degree longitude line. So obviously my figure is little tilted. This, yes. So line joining this center of mass, this will be 0-degree longitude, and any angle would go from like this to this. Okay, so lambda and phi are represented for this point as latitude and longitude of that particular point. So if anyone asks now from here onwards, how do you define latitude and longitude? First step, your earth is represented by oblate ellipsoid. Any point on the surface of earth, if you draw a normal, that will meet the equator, and the moment you get the intersection point to the equator, you can use that point to get the latitude and longitude. These latitude and longitude are known as geodetic latitude and longitude. Please remember the word geodetic. Why it is geodetic? Because you are using an ellipsoid to define this latitude and longitude. That's why it is called as geodetic latitude longitude. It could be geocentric also, but subject to you are not using ellipsoid. Instead, you are using sphere, which has been a very imaginary approximation of Earth's surface. Then only your normal would reach to center of gravity of the Earth. Okay. So this is first understanding about the lambda and phi. Any in this? Anyone who's having little doubt can explain it again. Again, if your surface is here, you have a point. So any point on this particular surface, you draw a normal that would meet the equator, this angle phi, this angle lambda, and it become lambda phi and h. Obviously h is above the ellipsoid. This above the ellipsoid you'll get the height. This is latitude, longitude, and height. Now coming back to your another discussion, where what is more important is this plane which is prepared here. This is the plane which is normally it has been inserted in this particular point. Although it is very difficult to realize it because it needs the 3D understanding, but from your imagination you can consider it. You can have ellipsoid in your hand and you fit in a normal section from a particular point. So this is the meridian, and from that meridian you are inserting a normal plane that contains this normal. Now it is very easy to realize. That means just like you have an apple and you are inserting a knife, a knife should contain the normal which has been drawn over that point. So this is called as normal section. Obviously, there are another normal I'm just erasing this. There is another normal which is against this point. Let's say this point. So this is another normal which is perpendicular to the meridian. Okay. So this is this section would another be that would be perpendicular to the meridian. So this is your meridian. Anything which is having 90° with respect to this meridian would be perpendicular to this meridian. Okay, but there would be another one which is a plane containing this normal. There is another one. You have to insert the plane such a manner that it contains this normal which intersects with the equator. So I hope now it is very much clear. So you have two kind of normals which have been realized. One is called as that contains the vertical, prime vertical, as well as the perpendicular to normal. Anyways, this normal which we are talking about in terms of meridian is from 90° to 270° because it goes from this way to this way. So you have 0, 180, 90, 275. Any doubts so far? Again, for those who have a little confusion but they are not asking, this is the three-dimensional figure where you have three axes. We'll discuss more about it later on. But you have ellipsoid, oblate ellipsoid, you have prime meridian, you have a normal section, you have a prime vertical that contains this normal. Okay, so that is meeting the Earth equator for latitude estimation. Similarly, here you have another oblate shape or section for your understanding, and this is meridian, point meridian. Again, you are just looking the point meridian, you know. And at any point meridian, if you draw a tangent, we are drawing tangent at point meridian. So what we are getting, and a normal to that tangent, we calling it normal to the meridian. This M is called as normal to the meridian. Please remember, we are introducing a new term here called capital M, which we call it normal
to meridian.
Sorry.
To meridian, sir.
Anyone speaking something?
No, normal to meridian.
Yes, yes, yes. Okay. And the value of M could be varying throughout the meridian, obviously, because you can see that at near poles it is different. Somewhere near equator it would be different. Okay. Although if you try to get the exact word, I would call it as radius of curvature in the prime uh, prime vertical to the meridian direction. That is the proper word. So we are getting the radius of curvature, because it is, it is the curvatures where we are drawing the perpendicular. This is your curvature where we are drawing the perpendicular. But what we are trying to find out, the radius of curvature in this prime vertical to the meridian direction. Okay. So this is another term which we have introduced as radius of curvature in the prime vertical to the meridian direction. So you just see meridian normal section showing the meridian radius of curvature. Okay. Here you have multiple circles, points, angles. We have phi, which we call it geodetic latitude. You have beta, which we call it geocentric latitude. You have psi, which we call it reduced latitude. Okay. But anyways, just for representation only, you can get what is M. M is A. You know A. What is A? A is major axis. E. What is E? E is your eccentricity. And how you can get the M value with the help of latitude. If you have the latitude with you, you can get this. Although the derivation you can do it anytime, so no problem. For more better approximation, this value is used very popularly. But you know what should be M? You should know it. It's very important. It is a function of phi, I would rather say. So M is a function of phi. Similarly, there is another figure. This another figure talks about the radius of curvature in prime vertical direction. Now there is two things which is very I mean, in this figure it needs to be very clearly visible, is that you have this as, this is your meridian, this is your tangent, then there is another meridian, you could call it, or section you would call it, that intersect this meridian at 90 degrees. So it is like that. You have this meridian and it is being intersect at 90 degree. Previously, we were simply having the tangent, and using that tangent, we were drawing the normal. So this is tangent at this point, normal. This is tangent, this point, normal. This is tangent, this point, normal. Here, we are one step further, and this is your meridian. This is intersected at 90 degree. This is meridian. This is intersected at 90 degree. This is called as prime vertical normal section, showing the prime vertical radius of curvature. We are also calling it N as a radius of curvature in prime vertical direction. So this point where it intersect this meridian at 90 degree, this point we get we draw a normal, and this is called as radius of curvature in prime vertical direction. This is your this point. Okay. So this is the N. How do we realize the N? So N, again, it is a function of phi. N is a function of phi, which we call it as A upon square root, again, major axis, your semi-major axis, eccentricity, latitude, and you get the radius of curvature in of prime vertical section, or prime vertical direction. Okay. Now, what is most important is, people would call it, so why do we need such radius of curvature in these two different directions? These are required when you try to convert or transform, what should we call it as, coordinate transformation. When you try to use the coordinate which are given in latitude lambda, phi, and h, and you try to convert the geocentric of x, y, z. That means the same point P, for which you have latitude, longitude, and height, if you want to convert it in a Cartesian system, we'll come back to this Cartesian system very soon. If you want to convert into this Cartesian system, how do we convert it? For conversion, you need something, isn't it? For conversion, you need certain coordinate transformation matrices, at where you will realize that this prime vertical radius of curvature in prime vertical direction will play its part. But anyways, this is just a basic introduction that both N and M are a function of phi. So you just look at this, because you know the function, you know the function name. Um, you could you could get this so-called value of M and N. You could see at 0 degree, that is at the equator, and at 90 degree, which is at the pole. For phi value at 0 at 90 degree. Please have a look. So I hope it is clear. Let us just have one little discussion about Euler's theorem. What it says that since what we are doing, we are simply having this conceptual understanding about prime vertical direction, both m and n, with respect to latitude. That means both m and n, they are function of phi, isn't it? But what if you have the azimuth information? Azimuth is always taken from the north. So if you have to measure the azimuth of any particular point, so you would look to north first, and then you rotate towards that point. That becomes the azimuth. So if you have a meridian section, that means the section that goes from north to south containing that particular point. If you have that one, you look to north one, and then you look towards that particular point for which you would want to have the azimuth. So if you are given alpha, then with respect to alpha, for at any point the prime vertical uh, radius of curvature in any meridional direction, which is m alpha, if you want to compute, it is a function of m, which is radius of curvature in prime vertical, and n divided by n cos square alpha plus m sin square. This we call a generalization of estimating the radius of curvature in any arbitrary direction alpha from meridial section for those cases where you have input as azimuth. Because many times the old scientists, they were working in the azimuth system. They do not have this so-called latitude and longitude every time. So they were working towards this azimuth direction, and for that we need to have such an certain conversion. For this m alpha serve that purpose. If you have that m and n, and then you can convert it to m alpha. It's just in generalization. Then there is a called as mean radius of curvature, is defined as the limiting case, that is m, the arithmetic mean of radii of infinite number of normal section, which can be drawn through a point, and our mean is called as square root of mn. I will least use somewhere, but anyways, this is for better understanding, it is available to you. Okay, so our main focus is the requirement of to define a coordinate system. Now, before this, let us think the need of ITRF, the need of Everest, or need of any coordinate system. What were the need? Need is to define a point. Now, point definition requires a proper reference. So any coordinate system that you need to define from here onwards would need these three things. One is location of the origin. Another is orientation of the three fundamental axes, and then parameters which define the position of a point referred to the coordinate system. Okay, so generally we call it as a 7-parameter requirement. Why it is called a 7-parameter requirement? I'll just tell you some basic concept about those things. 7-parameter, 3 for origin, 3 for fundamental axis, and 1 for scaling. So these are the the 7-parameter requirement for defining a coordinate system. Okay. Now for defining coordinate system, anyone can define its in its own way. Okay, you can have it your own convention to define the coordinate system, just like you were having in the case of height system. You were having your own convention, but eventually you realize that MSL is serving its purpose. Okay, you have many discussion. In fact, any book on geodesy, the first chapter talks about this, how people reach at mean sea level. I mean, there is a process. Nobody just jumped to mean sea level directly. There is a lot of scientific involvement is there. Then people reach at mean sea level. Similarly, here also, you can have your own coordinate system, no problem. But how to define a coordinate system, you need to first realize it. So any coordinate system needs origin, fundamental axes, and scale understanding. But this is that by definition you can have it. But let's say, for example, I'm interested in finding or realizing defining a coordinate system which has its origin at center of mass of Earth. But can I go to center of mass of Earth? Can I see it? Can I feel it? No, because it is constantly varying. Every time, every instant, it is varying. Because mass density of Earth is not something which is fixed in nature. It is varying in nature, which you can already see it. So just by saying, I want an origin to be at center of mass of Earth would not serve the purpose. You have to realize it also. Second thing, what do you want your z-axis? Somebody say, I want z-axis to be Earth rotation axis. But is it stable? Answer is no. It is not stable. You cannot just feel it that it is just crossing the exact 0 degree north. No, it is not. It is very, very deviated from that. So my point is, you can define coordinate system in your own manner, but the beauty is how to realize it scientifically. And for that matter, we are talking of establishing the geodetic infrastructure throughout the globe so that whatever we are defining, we could realize it. Realization is very important. These ITRF is just a realization of this convention by which we are defining our coordinate system, the geocentric coordinate system, which we are talking about. Okay. So this ITRF, which we call it International Terrestrial Reference Frame 2008, it's just one realization of our coordinate system, which I said I wanted the origin at center of mass of Earth. The z-axis should contain the Earth rotation axis, and so on. Please remember this ITRF. When I say ITRF is nothing but a group of points, well-defined points, which are thoroughly monitored by several stations, several co-located techniques at one place. Okay. So as I've mentioned about VLBI, SLR, LLR, your GPS, or maybe some other beacons, the Doris, they are all possible techniques. But how do you realize it? You realize by these stations only. So at present, you have 380 to 400 such a station around the globe, which are forming a catalog of points, velocity, acceleration, everything. Okay, that are defining or helping us to define our coordinate system, which would be consistent throughout the globe. That means everyone in the United States, in India, in Japan, in Australia, everyone should be referring their result to that same datum. Then only the intercontinental crystal mechanism, the sea level variation could be visualized and you could arrive at a common conclusion. You understand this part? Because it is not like, some Australia is doing something different, we are doing something different, and then we can say, okay, we have got this. They are saying we have got this, but there is no one. How society would believing the scientific community when they arrive at a common conclusion. Okay, so please understand this requirement of coordinate system is very much there. That's why the Survey of India have adopted the ITRF, because many a times what people are with now, everyone is having GPS. Its coordinates are coming in WG74, ITRF, and everyone. and you cannot work in two different systems at the same time. You have to work on a common system. That's why they have adopted this 3D geodetic system of ITR, because they do not want any such confusion from their part to the community. Okay, it is their responsibility also. Okay, anyways, so what we were doing, we were defining the coordinate system in with the help of these 7 parameters. One is 3 for origin, 3 for fundamental axes, as well as 1 for scale. Okay, I hope it is clear. Any confusion you can have. Okay, so this is very wonderful figure of your coordinate system which we are talking about. Okay, so you have the ellipsoid which is best fitting the earth. Then you have a frame. Frame, you could realize now. I'm just saying step by step. You can do it. What you want is that you just need to have a globe in front of you. You have seen, all of you have seen the globe. That would be sitting on a table of an bureaucrats or any officers. So just use that globe, take it out from its frame. Okay, you just have a globe. What you want a welded frame of XYZ, which just as shown here, inside it, such that the center of mass of that globe coincide with the origin of this frame. You just want this. So you have a globe that is fitted such that its center of globe meet this frame of origin. So this means what I'm talking about is this should be inside the globe, and you have a common location for that origin as well as the center of mass. Then obviously while inserting, you would see that there are 3 points where you need to, oh sorry, uh, you need to weld it again. So this is welded here, welded here, welded here. That becomes the concept of ECEF frame. Why? The requirement of ECEF, because nobody wants to have a confusion or overlapping coordinates to 2 different points. What you want? Every point should have its unique signature, unique ID, unique coordinate. Okay. So for that, you want a system which is earth centered, earth fixed. When you have centered it, it is earth centered. When you have fixed it, it is, now it rotates with earth. Now it doesn't vary. Just realize, if your system is not fixed with earth, what will happen? The point which you are having today, maybe after 10 years, United States would be having the same point location, which you do not want. You do not appreciate that scenario, because you have to come back again to the same place. You have to work again. So that's why it should be earth centered, earth fixed. Okay, first point. Second point is the poles, which is the primary pole, secondary pole. Primary pole is that z-axis, which the axis of rotation of the earth is the tertiary axis. The primary axis is x. Okay, but the primary pole is z. Okay, so, and this Greenwich meridian, which intersects the earth equator, which I have already explained, so no need to go back again. The only issue remains with the y-axis. How to define the y-axis? So it could be defined uh, by your convenience. How do you conveniently want your system to be? So some people said right-handed, some people said left-handed. So anyway, you can define it on your own manner. But the right-handed coordinate system is very popular, and people are usually following it. I hope it is clear. Okay. Then the problem lies with the how to define, because x-axis is very simple. You have a Greenwich meridian which intersects the equator. That become intersection point would become joining with the origin would become x-axis. Conveniently, you have z-axis which coincides with the earth rotation axis, and you have right-handed coordinate system to mutually perpendicular y-axis. But the problem is you do not have the rotation axis stable. That's why the Z has to be realized by some convention. So the two convention have been adopted by scientific community. One is called as CIO, another is called as CTP. These are the two conventions that has been adopted by international associations, so that CIO full form is conventional international origin. Why? Because people now know that the CIO is varying in nature. It has to be averaged. So by convention, they have defined this origin, CIO. Conventional terrestrial pole, that means this primary pole. This is also varying in nature because Earth rotation axis doesn't coincide with the 0° north, or it doesn't come out directly at 0°. It is shifted a little bit because of the various gravitational attraction and because of the internal mass density. The z-axis is not at its actual position. It is varying, and it is varying in a cone like this. It has to be here, but it is not here. It is varying in nature. It is revolving. There is a wobble in that z-axis. So people realize that since by convention you cannot every time have a different z direction, so by convention they have adopted this conventional terrestrial pole also, that we are averaging some 5 years of data to fix this CTP and CIO. So generally in your literature you would find that from 1900 to 1905 it is written that the average value of rotation axis was taken and is defined as CTP. So by convention it has been decided. Okay, but if you talk about what is present scenario, it is towards it some international instantaneous. I'm again just drawing because figure already have some demarcation. We do not need to again do it. If I tell you, actually the Earth axis is like this. And let's say at any point it is denoting here. At this point it is only. But for convention purpose, what we want this so-called we need to define it by convention by taking the averages. Okay, so I hope you get the understanding. You have Earth, you have three fundamental axes. Your axis has to be defined by conventions. Why? Because by convention, if your conventions are not stable, how can you realize it? Okay, but practical scenario is very different. Practical scenario is different in the sense that you do not have the so-called uh, Earth rotation axis at 0° north. It is slightly tilted, and that tiltness is studied by scientific community that are studying the polar motions. Now all of you are sitting somewhere on your seats, so just go back, just have an escape velocity to your chair or something, and go back into the space. How do you see the Earth? You do not see Earth like this. You see Earth like this. It is slightly tilted and it is moving around the ecliptic path around sun, isn't it? But if you closely observe, have a zoom in your eyes, what you feel? It is wobbling. It is not rotating, it is wobbling. If you are more interested, you can go back in your YouTube and just see how the Earth wobble in space. You will see a very nice picturization of a 3D wobble in Earth. Earth is also rotating. It is also revolving around sun. And in that process, because of several gravitational attraction from sun and moon, and in an internal mass redistribution that is constantly going on, what is really happening? Earth is trying to slow down. From last few many years, Earth has been slowed down by the solar system. If you talk about a solar time system, if you talk about that, from 12 to 12 it has to be 24 hours, but it is not fact. In fact, your Earth has been slowed down by 34-35 seconds. Do you realize it? Your Earth has been slowed down by 35-36 seconds in last from 20-25 years. Okay, anyways, you'll come to know more about this inertial space understanding and how to look at the Earth from inertial space in next semester. But anyways, we just have to define the coordinate system. That's it. Okay. So I think most of you have got little more understanding. Any questions so far? Any questions? Okay, so I think with this we'll stop here, and tomorrow there is an announcement for all of you that tomorrow there will be a first we'll have little discussion on the our content which we were covering, and then after that there will be a quiz. Two quizzes will be there back to back. One on elementary probability concept which you have discussed, and then second on obviously with the error propagation. I've uploaded the slides also on error propagation to your teams, as well as some basic concepts related to matrices. I've uploaded new content which you can go through, and I hope you are going through the so-called assignments which I've given to you. I have extended one deadline by one more day. Now deadline is Friday. You can submit it by Friday. You can more focus on revising the content so that you could perform well in your quizzes. Your quizzes marks will be added in your final grade, so it is highly appreciated that you should revise your content properly. And quizzes are on both mode. One is objective as well as subjective. So objective is very clear. You just have to write the option, and the subjective you have to perform it based on your understanding that has been developed. Okay. There will be no repetition of the quizzes. Those who are absent will be marked 0. So it is highly advised that you should attend your quizzes on time. Okay. And gradually before your mid-semester break, we will try to finish the schedule, and we'll try to finish the whole content of error propagation and some of the accuracy measures which I have to tell you, which we have skipped from the first discussion point from elementary probability concept. That will cover it up. This is very required. You should know the understanding of 3D coordinate, 3D accuracy measures which are popularly used, 1D, 2D, 3D, both, and some of the basics of balancing of accuracies that will cover. So by mid-semester recess, you will be having this much content, and apart from that, there is assignment which you have to upload. And if you have any queries, you can always ask to me as well as the TA for this course. Any questions if you have. And then next Wednesday, you will have quiz on the content which I'm teaching right now about the coordinate system, basics of coordinate system. For that, I'll upload certain content to your teams. You could read that content, and based on that, we'll have a small quizzes about your understanding in the coordinate system also. Okay. Any questions so far?
Hello, sir. Is there a book for this lab?
generally, beta, there is not a book, but yes, yeah, I wanted to show you something. Okay, just a moment. I'm just opening it up. Yesterday I wanted to show it up, but अच्छा रहा आपने याद दिला दिया. मैं एक मिनट आपको ओपन करके दिखाता हूँ. See, that is the beauty of I mean open access. That nowadays, what is really happening is everything is you have to purchase. But some universities are doing a wonderful job. What they are doing, they are opening their all resources to students. Just a moment. I hope the screen is visible. Sumit?
Yes, sir. Screen visible.
Okay. So this is the website of Ohio State School of Earth Sciences, where they are running this program. I think I have shown you earlier also. But when you go into the resources, which I recently visited this website on somewhere last week, and I realized that they have uploaded this two books. One is uh, Geometric Coordinate System in Geodesy by Christopher Jekeli, and yes, this geometric reference system in geodesy, if you go back and download this, it's very good book, very nice book. Some of your concepts could be improved on understanding of coordinate system. See, they are initially, this is about talking about the primary mathematical relations, reference system and frames, the earth shape. Then they are going back towards ellipsoid and geodetic coordinate, basic ellipsoidal geometry, ellipsoidal coordinates, elementary differential geodesy, radii of curvature, normal section, azimuth geodesics, which I have just explained in fact. And then transformation from geodetic to card, because all these are required. The radii of curvature in prime vertical directions, meridional direction, they are all required for transformation between geodetic and Cartesian. Then obviously, initially there were people were doing the so-called observation to stars and various celestial objects. So that comes into the astronomic coordinate. So you don't have to read all, because we'll be covering some of the content in next semester also. But you have celestial system, which we were talking about. Then you have terrestrial system, the horizontal datum, geodetic datum, vertical datum. Okay, the more details about the celestial system, which you can skip, the time system, which we will be covering next semester. So it is not simply as a book. It is a note. It is a notes of compilation of notes for which the professors at Ohio State have taught in their classes, and it is more like a book, but you can try to see there are a lot of content is written in terms of equation explaining everything, the reference system, reference frame, the reference earth shape, the this Eratosthenes, and then there may be somewhere in they will be talking about the ellipsoid when the coordinate system in geodesy. Uh, this figure is being taken from that I've shown is taken from here only, and very basic, the ellipse construction, flattening, everything is explained here. These are the table which I've shown you also: Airy, Everest, Bessel, Clark, Modified Clark, Krakowski, Mercury, GRS, Modified Mercury, Australian National. They have their own data until ITRF came. So at the last you have IRS, ITRF. It's a very good book. You can download it, because it is, I've shown you the website, that you go to Ohio State Geodesy, Department of the School of Earth Sciences, and you can go to resources, you can download it. So it is mostly about the basics content. This figure which I've shown today, normal section. So I think this is one good book which you should download it and you can refer to. See, I understand that from day one it is not possible that you would grab every little content, but when, when you come back and read it again many a times during your quizzes and your concept building, this book would help you a lot. Okay, so some of the figures are very well prepared. In fact, when you go back into the celestial coordinate system kind of mechanism, very nice figures are there. Then problems are also there, which you can try to see. So I hope it is very much clear. Now, the very much important point, which for which I should have shown you tomorrow also, yesterday also. This there is a book called which is uploaded by in September 2021. You could see here this book by Adjustment Computation by Kyle Snow and Burkhard Safrin. Burkhard Safrin was the leading scientist of so-called adjustment computation, and this book has been recently been uploaded. And this book is also a notes compilation of notes, which you should download and refer to. Very nice book. Although it will not take much time, it is only 2 MB. See the title, Adjustment Computation, and you can follow it from day one because a lot of content have already been taught. You could see here the foundation, observation, parameter, random error, essential math, the basic math, stochastic properties, matrix algebra, random variables, the basic probability concept, the multivariate, univariate problem. Then we'll after your maybe your recess or before recess, we'll start this method of direct observation. It's a very good book. You could see here from here. I'm just going through the initial content, the part one, adjustment computation, parameters, observation, fixed parameter, modules, the functional relation, the stochastic relation, okay, and the variance covariance matrix, weight matrix, the expectation operator for errors, the basics, the matrix algebra, important concepts are given. Then related to that problem, then random variables, the review from statistics, the cumulative distribution function we have covered, probability density function we have covered. This book you can follow. I mean, I don't find any kind of hindrance in this book to be followed. It's very nice book. The standalone distribution you all have done. You have in fact you have given proof also for these indexes which you have prepared. These are all 0.68, 0.3, 95.5. You all have done. So you'll appreciate it the moment you read the expectation operator, which they are explaining for univariate case, for bivariate case, which we have done. In fact, they have similarly to us, they are also giving proof for various related the dispersion index, the expectation index, the mean squared error, the multivariate case. So all is, I think you can go ahead. See the expectation of ay plus rho or gamma, whatever it is a into expectation of y. You know that dispersion, law of propagation. If you have a function of ay plus gamma, what you write? A sigma xx a transpose. That's how you do it. So it is very simple. You can just see the correlation matrix. Only thing, they have just properly followed the conventional way of writing it. But you can simply start from your day one with this concept. So this is uploaded on September 21. You are lucky fellow that you got this book. You can just have access to this book. A model. We will start this, and you will be from day one. You will be quickly solving problems related to level, related to a lot of very in these type of so-called derivation you will be performing in your classrooms only. See, if you work in lidar, remote sensing, in anywhere, if you have the data, you have to do the adjustment. That's it. End of the story. I mean, without adjustment, you cannot move ahead. Otherwise, you will be working with errors. Your results is will be considered as garbage. Okay, you may get something out of your expectation, but until unless you prove with respect to the uncertainty from adjustment point of view, you cannot move ahead. So it's very nice literature is available. So you can download these two books and refer it.